Okay, welcome to our next lecture. What I wanted to do is there were a few questions I've gotten during the last week about some homework, so I wanted to make a few points a little bit more clear. The last column on the spreadsheet needs a little bit of fiddling to determine the sealed conditions. So you need to do a little bit of fiddling with that to make it work. It wasn't in the original spreadsheet, and it requires a little bit of adjustment. You need to make the total volume equal to 1. So you need to use a goal seeker solver to make the total volume equal to 1, and that'll give you the water to cement ratio for that column. The other thing that I wanted to point out was there was a question related to capillary porosity versus gel porosity and how they were related to the water to cement ratio. Capillary porosity is just the volume of the capillary pores divided by the total system. Gel porosity, you can get to understanding the question a little bit more if you want to look at the volume of the gel pores divided by the total volume of the gel, which is the volume of the solid plus the volume of the pores. So hopefully that will help you to answer some of those questions if you're going to go the route of trying to calculate it out. Okay. Other questions as it relates to homework?
What do we mean by empty pores?
Does it include chemical shrinkage or it doesn't?
Empty pores will typically include chemical shrinkage, capillary pores, and even gel pores if we dry it out. So the easiest way to answer that question would be to talk about the 3 types of pores, and then you could calculate the total volume. Other questions as it relates to the homework? Okay, so let's jump ahead and let's talk a little bit today about aggregates. We've gotten through some of the work on supplementary cements. We've talked about cement in general. We talked very briefly about water last class. So there'll be a very short homework from last class that'll be posted on Wednesday. I'll try to give you one homework each week so that we stay somewhat current. We're not going back 15 lectures to try to figure out what I was talking about a month and a half ago. What I want to talk a little bit about today is I want to talk about aggregates. I want to talk about aggregates today mainly in terms of production and a general overview. On Wednesday, we will talk much more about the properties of those aggregates. But today I want to start off with production. If we have some time, I'll get into durability issues with aggregates. But I'm going to talk a little bit about the basics. I'm then going to go into some of the aspects of aggregate production that you may want to be aware of. And then if we have time, we'll do durability problems. On Wednesday, we'll finish the aggregates up, and then we'll move on to mixture proportioning. One of the other things I wanted to point out is you'll notice on the website that I know Ryan is very concerned about things like this with the 135 slides that are in the lecture on mixture proportioning. They will cover more than one lecture. I will slow down as best I can to at least make 135 slides last for 2 hours. But what you'll notice is that the whole package is presented as one, and then I'll just start and stop as time permits in class. I thought before we jumped into aggregates, it would be good to sort of have a hall of fame of all the famous aggregates or all the famous rocks over time. So we've listed a few out here. The Pet Rock, which is probably the most expensive aggregate that's ever been produced. We've got The Rock, who seems to have gone from a wrestling superstar to a lousy actor in many of the newer movies. We've got Rocky and Bullwinkle. We've got Rocky, who's probably going to come out with Rocky 38 soon. Rocky fights from his grave or something like that. We've got The Rock, Alcatraz, and we've got Twisted Sister, who let us all know that they just wanted to rock. And this is about as much excitement as I can put into a lecture on rocks, but I will try to do my best from here on out. What you will notice when we start to look at the typical volumes of some of the constituent materials that make up concrete, we spent a lot of time talking about cement. Cement makes up a relatively small portion of the overall volume of the system. So this is just a couple bar charts of the total volume made up inside of concrete. You'll notice that cement we've spent a reasonable amount of time talking about, but it's a relatively small portion of the volume. The reason we spend a lot of time is because it's really the most interesting component. It's the component that's actually doing something. It's the glue, it's the binder, it's what we're changing when we add supplementary materials. It has the porosity, it controls the strength. It's a really important overall constituent material. Water will make up another important part of this, and again, it goes into making the binder. It goes into defining things like the workability of our fresh concrete. We've got our air. This will either be entrained air that we put in on purpose to help us out with freezing and thawing, or air that just comes in as a bonus due to the mixing process. And then the remaining portion of the system we break up into little rocks and big rocks, coarse aggregate and fine aggregate. And depending upon the leanness or the richness of the mix, you'll notice that we go from something that may be around 54% aggregate by volume, and I will tell you, if you're making a commercial mix where you've got 54 volume percent aggregate and the rest is paste, it's going to be a mix that is likely going to have some problems. It's also going to be a mix that's likely going to be expensive, up to a mix where we may be looking at something like 76, 78% aggregate. So you'll notice that the aggregate is a fairly large portion of the overall volume of the system. The aggregate's going to be in there really for two reasons. The first reason, which is a very practical reason, is the aggregates are going to help out with the economy of the overall system. Aggregates are going to be much cheaper than a lot of the other components in the system, so the goal is really to try and to throw as many of the cheap components in as possible. So try to fill up the volume with the aggregates because they're the least expensive. The second thing that the aggregates are really going to help us do is the aggregates are going to provide dimensional stability for the overall concrete. So we're actually going to use this filler in a beneficial way. There are a lot of people who say, well, why don't we just use paste and water? If we use paste and water to pave a highway, it would be a disaster. There'd be cracks everywhere. It would be incredibly brittle. The temperatures would rise to levels where we'd be boiling out the water. So we really rely on the aggregates not only as a filler to help us with economy, but they're also going to make the system a lot more stable. They're going to help us to reduce the overall heat that's generated per cubic yard of concrete. They're going to increase the toughness of the system. They're going to confuse the cracks. They're going to make the cracks move around. They're not going to go straight through like we would have if we had a straight Portland cement paste. So the aggregates are really a vital component to the overall system, and they're not just a material that's in there to occupy space, but there actually is a benefit to having them in the overall system. Now, aggregates are going to be related to a lot of properties, a lot of different properties. Freezing and thawing, aggregates are going to play a key role, and here we're not necessarily talking about the freezing and thawing capacity of the concrete, but we're really looking at the ability of the aggregates themselves to respond to freezing and thawing. A lot of you have driven on roads where you'll notice that there are quite a few cracks in different types of pavements. A fine example of this would be if you leave campus and you drive out to the mall and you head over on 26, you'll notice that every 18 feet your car bounces up and down because they've replaced the joints. And then you'll get into a section where your car will not only bounce up and down, but it'll bounce up and down and chatter like crazy because they've yet to replace those joints. Those are aggregate problems. That is a problem called decracking that we will talk about a little bit later. That's a fairly common problem where the aggregate itself isn't resistant to freezing and thawing. And this is a big issue, and this drives a lot of how aggregates are looked at and how aggregates are brought into the mixture. Length change. One of the most important things that aggregates will do is they will help in the volumetric stability. They will help in shrinkage, but they will also help a lot when we talk about temperature changes. So the coefficient of thermal expansion will be made up of a composite. We've got a composite material. The coefficient of thermal expansion will be an average property of the cement paste and the aggregate. Now, when I say average, we're not talking a 50-50 average. If 80% of the system is aggregate, 80% of the coefficient of thermal expansion is aggregate. So you'll notice that the aggregate plays a big role in the coefficient of thermal expansion. It also will play a big role in determining things like the elastic modulus. So buildings like Trump's building in Chicago is going to be dictated heavily, the design of that is dictated heavily on the stiffness because it's such a tall building. It's in a high wind area, so the stiffness had to be a certain amount. The aggregate that's used there will make a big impact on the stiffness of the overall concrete. The stiffer the aggregate, the stiffer the overall composite's going to be. There'll be other reactions that can take place. Alkali silica reaction, alkali aggregate reaction. Here's where there's a battle going on between the alkalis that are coming off of the cement or that are coming from the fly ash or coming into the system in fluid, reacting with the silica that's inside of an unstable silica form that could be inside of the aggregates. And this is a big issue in quite a few structures, because once it starts a cracking process, once it starts the damage and degradation process, there's very little that can be done to retrofit or repair this. There's a lot of research going on into figuring out ways to stop ASR problems once they start, and to really go back and retroactively try to fix that concrete to prevent that reaction from occurring even more. Mass concretes, the aggregates are going to be incredibly important because they're going to dictate things like the thermal conductivity of the concrete, how quickly it gives off heat. They're going to also dictate how much cement is in the system per cubic yard. So they're going to have a big impact on how much heat is developed in the concrete when it hydrates. And you may say, well, the aggregates aren't doing anything, they're just sitting there. They're either sitting there and holding heat, or they're transferring heat, or they're not taking up space, or they are taking up space that the cement wouldn't normally be in. So if you took a cubic yard of cement, it's going to generate a lot more heat than a cubic yard of concrete, because there's more cement in the system reacting. So that the aggregates can basically act to cut down the volume of the paste that's in the system reacting. Economy, we mentioned before, one of the cheapest components of things that we're putting into our concrete is the aggregates. Right? They are going to be much less expensive than the cement. The paste content, again, the more that you can reduce the paste content, typically the less money you're going to be spending on the overall concrete. And this will come down to the size and the gradations of the aggregate. Strength is going to be influenced by a few things. The actual strength of the aggregate itself, the size of the aggregate, which we'll spend a lot more time talking about later on in the semester, and the texture of the aggregate. A smooth aggregate is going to stick to the paste not as well as a rough aggregate. So the surface area, the way that it's crushed, is going to make a big difference in how well it bonds and what the overall strength is. And then sometimes you can get an aggregate surface that'll polish. So you'll put the concrete down, and then over time the concrete will start to become slippery, because the aggregates will be polishing under, either stopping traffic or something like that. And it's a real big problem when you start to look at traffic safety. So you want to make sure that your aggregates don't polish, don't become slippery. And this is a big important thing to look at. Now, I've put one of my favorite characters of all times here. And does anybody know who's down in the lower corner? Does anybody know the comic strip he comes out of? The evil guy in Rocky and Bullwinkle. And he had a name. His first name was Boris. Yeltsin. And his last name was?
Boris.
Boris? No, he was not Boris. He was Boris Badenov. So you'll remember Rocky and Bullwinkle are at the height of the Cold War, and that's just a bad-sounding last name. Well, I put Boris up here not only because he's one of my favorite characters of all time, which likely gives you a little bit of insight into my personality, but it's really the state of aggregates in concrete today. We really want to start trying to use different types of aggregates, because we're running out of the aggregates that are really, really great aggregates. So the question is, much like Boris's last name, can we use aggregates that are just not bad enough, or just good enough aggregates that we're not going to end up with a problem down the road? Marginal aggregates, aggregates that people wouldn't have used 20 or 30 years ago, all of a sudden are looking fairly attractive to the concrete industry because of the lack of supply that's out there for good aggregates in many places, and the fact that we have a lot of these aggregates. There are a lot of quarries that are already open with these aggregates out there. Can we find a way to use them? One of the things that I will point out is there are a lot of these aggregates that actually have sort of beneficial properties. So 20 or 30 years ago, you would have seen a whole quarry that was condemned because of the pore sizes of those aggregates. There's actually one of these in Indiana, and we had a student who was doing a research project on it. We found the aggregates. They had exactly the ideal properties because they gave up water really easily. So they're a lot like a lightweight aggregate that we'll talk about later on in the semester for internal curing. Turns out that at the time in the 60s, the quarry was actually shut down because it was really hard to keep water in the aggregates. So now we're actually looking at some of the beneficial properties of these aggregates because it's really easy for them to give up water in certain applications. You're seeing a lot of people trying to look at these materials and say, can we repurpose these materials? Can we use them in a different way that may make these materials usable, may make them very beneficial, where we can actually get some benefit out of using these aggregates. Now, aggregates or rocks are a quote-unquote inert filler. And I say inert because what you're going to find out as we keep talking about here is the best that you can hope for is the aggregates to be inert. The best that you can hope for is for them to sit and sleep for the rest of the concrete. If they are not inert, if they are going to be reacting with the cement, they're going to be reacting with the alkalis, you're going to have a big problem. All right, so we're hoping that they are inert. We're hoping we're not going to have freeze-thaw problems. We're hoping we're not going to have an ASR problem. They are an inert, relatively inert material. They're going to increase the dimensional stability. Typically, they're going to increase the stiffness. In some regions of the world, they're going to limit the strength of the concrete that you can produce. So, for example, in India, the aggregates, I believe, are typically the limiting factor on some high-strength concretes. Right? The toughness of the concrete is going to be dictated by the size of the aggregate and the type of the aggregate. You will find that as the size of the aggregate decreases, the material becomes more brittle or less tough. They'll also provide the wear resistance, the resistance to things like studded snow tires, or the resistance to polishing when traffic goes across them, or in the state that I grew up in, the resistance to horses traveling across the concrete. And believe it or not, the horses in Amish country do a number on asphalt and concrete pavements. So each year there are research projects in Pennsylvania that are dedicated to horse interaction and trailer interaction with pavements because this is an important problem dictated by the aggregates that are in the overall system. As I mentioned, they're going to occupy 60 to 80% of the concrete volume. As a general rule of thumb, you're looking at something in the order of an eighth to a 20th of the cost of the cement. So it's much more economical. And I will give you the ASTM C33 definition. C33 is the rules, or are the rules, is the rules, am the rules, whatever the proper verb is there, for what an aggregate is. Aggregate must be clean, hard, strong, durable, free of absorbed chemicals, coatings of clay, other fine materials that could affect hydration, bond, or cement paste. Now again, that's an ideal aggregate. Many times if we start looking at trying to recycle old concrete and using it as aggregate, it may have absorbed chemicals in it. We may run into aggregate seams that have clay in it that we need to figure out how to use. We may have aggregate that's not that hard or that strong, and we need to figure out a way to use it. So these are things that we should be keeping aware. This is sort of an ideal definition. We may end up having to use aggregates that are a little bit different and trying to design ways to do that. Aggregate, for the most part in the concrete industry, comes in two flavors. Comes in a fine aggregate flavor and a coarse aggregate flavor. Little rocks and big rocks. For those of you who want to take this out of a graduate course and use it in the field, we're talking about the little rocks or the sand. Typically we're looking at something here below about a quarter of an inch, below 5 millimeters. This is typically going to make up somewhere between about 35 and 50% of the overall volume of the aggregate in the system. The big rocks, the coarse aggregate, are typically going to be our gravel, our crushed stone, the larger types of rocks. Here we're talking about aggregate that is greater than roughly a quarter of an inch, 5 millimeters. And we're looking at something that may be going from about a quarter of an inch to 3/8 of an inch, or all the way up to 1.5 inches or 2 inches. In the late 1980s, early 1990s, all the rage was to make the aggregates smaller. Smaller aggregates, smaller aggregates, smaller aggregates. Any guesses why we wanted to make them smaller? Guys who own crushing plants were really good salesmen.
More homogeneous area.
More homogeneous, and as the drive was to increase strength, the more homogeneous the aggregates are, the higher the strength typically is. So the smaller the aggregates, the strength of the concrete typically goes up. Any other reasons why they wanted to make it smaller? For example, in the state of Indiana, driving on Road 26 out to the mall, every 18 feet, Your car undergoes that joint, a lot of joint damage. One way that you can make the aggregates more resistant themselves to freezing and thawing is to classify the aggregates, but also to use smaller aggregates. Bigger aggregates are more susceptible to things like decracking. They're a little bit harder to mix into the system, so there was a big drive to use smaller and smaller aggregates. Now, you will see, like most things in the concrete community, the pendulum has shifted backwards, and people have said, why are we using these small aggregates? We should be using larger aggregates. Why would we want to use larger aggregates now?
Less
Other
energy.
than the fact that people can't read journals that are 15 years old.
Saves
20 years
energy.
old. It saves energy of crushing. Has another big benefit. Has more or less surface area. Big rock versus a small rock.
Less area.
Less surface area. So we will see what the effects of less surface area is. The key adjective here is going to be coarse and fine. Now, you will hear a lot of people talking about trying to go to 3 aggregate, 4 aggregate, 5 aggregate systems. There are places where they will use intermediate size aggregate, but for the most part, most plants are set up to do coarse and fine, and it's really kind of a big issue to start trying to add something additional in to the system. When we talk later on in the semester about ready-mix plants, I think you'll see a little bit of why for a conventional ready-mix plant it's a little tricky to add in a different aggregate size. In addition to being classified by size, aggregates can be classified by their density. So they are either normal weight aggregates, which we'll be seeing here about 95 to 105 pounds per cubic foot. They will make a concrete that is about 145, 150 pounds per cubic foot, which is our typical unit weight of concrete. You will also see that aggregates will be fat aggregates or heavyweight aggregates or light aggregates, lightweight aggregates. Lightweight aggregates, the main use of them is going to be what a tough Monday. Concrete canoe. Yeah, there's a huge market for concrete canoes, so that's where we're going to use these. All right, we will find out that there are concrete canoes, concrete battleships that use lightweight aggregates, but the big thing that drives lightweight aggregate, at least historically, has been reducing the self-weight of the concrete. If you're designing a bridge and the majority of the structure is to hold the structure itself up, that's not a very efficient design. So they switched to lightweight aggregates to make the girders lighter, make the bridge deck lighter, so that you can make the bridge design much more elegant. The other thing that I will point out here is there is a dramatic excitement going on in the industry, especially the lightweight aggregate producers have found out that there are benefits to curing concrete when they use lightweight aggregate. We'll talk a little bit about this later on in the semester. So there's a lot of people using lightweight aggregate or other types of materials that they can actually either make the material sound absorbing or they can make the material self-curing, internal curing. We'll talk a little bit more about this later on in the semester. There's also the heavyweight aggregates, as we pointed out. The heavyweight aggregates typically have one industry that's really, really excited about them. There may be things like anchors that would get excited about it, but that's typically not the big issue. The real big issue for heavyweight concrete is, for which one? Counterweights? No, you'll occasionally, but it's just usually easier for a counterweight to just put more of the concrete there than to get involved in a lot of other stuff. It's a word that our current president can't say. It's an industry that is back on the rise. I know there's so many of them that are out there that he can't say. Nuclear. All right, the nuclear industry is very excited about heavyweight concrete because it can help in shielding. So typically they will replace the normal aggregate with a much heavier aggregate, like maybe a steel aggregate or something like that, that'll go into the system to really increase the density of the system with the idea of shielding. There'll also be quite a bit of recycled aggregates coming out, synthetic lightweight aggregates, other things that we'll talk about as we move forward. These are naturally occurring rocks and minerals. Obviously, you've got different types of rocks, igneous, sedimentary, metamorphic, and we will look at, as we go through, and each one of these has its own issues when we start to talk about durability and we start to talk about other processes inside of concrete. Fine aggregate, we're typically looking at a natural silica sand. This can be as easy as opening up a seam and having the sand ready-made. More recently, there's been quite a push to using crushed sands in concrete. Coarse aggregate, you'll see that there's quite a bit of gravel used. There's also quite a bit of crushed rock used. Most of the crushed rock tends to be carbonate rock. About a third of the crushed rock is other types of rock that's being used. Aggregate strength, generally we do not test the strength of the aggregate. So if you went to all the producers in the state of Indiana and you asked them what's the strength of their limestone, they would probably look at you like you have no idea what it is you're asking, because they've never been asked that question before, because they don't test it on a regular basis. Generally, we don't test the strength of the aggregate, but I've given you some general properties in the table over to the right. Paste and bond properties are generally much more important. The tensile strengths of these aggregates ranges from about 2 to 15 megapascals, so it's going to be roughly about the same as what we're talking about in concretes when we get to that. You will notice that the compressive strength will have quite a wide variation depending upon where it's tested and the orientation of the defects in those aggregates. And the elastic modulus will be generally something that's very important that we're looking at. Now, there are a few simple rules of thumb. Generally, if you've got quite a bit of siliceous particles inside of the system, it will be fairly good for skid resistance, won't have a polishing problem. So generally, if about 25% of the system is siliceous, you won't have that problem. Another thing, if you're not so sure about the aggregate and its resistance to freezing and thawing, one real quick measure, if you've got some local information on this, the ratio of wet to dry strength can tell you quite a bit about the durability issues. It tells you quite a bit about what's inside of the aggregate and can tell you a lot about durability. Most of the time, we will be looking at durability issues based on local history. So in the U.S., there's very few places where there won't be some existing knowledge on a particular aggregate. And one of the best ways to know is this a good aggregate source is to look around and see where that aggregate has been used locally. And local producers will know that there are good aggregate sources and there are bad aggregate sources. This is not usually a well-kept secret, but a lot of times people will say, oh yeah, that's really good aggregate, and the rest of the aggregate they'll sort of look and they may curl their eyes or may give you something else when you ask about that particular source. And the sources do not have to be so far apart from one another to be a real good seam or a real bad seam. In one of the quarries that I'll show you that I worked in, there was a fantastic seam located no more than a quarter mile from a seam that really had some issues. So you really need to be careful when you're looking at this.
Is this why the rocks in India is their compressive strength a lot lower?
Their strength is lower. So a lot of times what you'll see is when they hit the limits on their high strength concrete, they're fracturing the aggregates. And once you start fracturing the rock, there's very little that you can do to increase the overall strength. I mean, you can still get there with the paste by increasing the paste, but it's really sort of a law of diminishing returns. Other places, if you go to Seattle, they have fantastic rocks. Chicago has great rocks, and what you'll see is in Chicago, high-strength concrete is not a big deal because they've got, fantastic sources of aggregate. In Seattle, high-strength concrete is not a big deal because they've got great sources of aggregate. So you'll see that the aggregate plays a big role in what you can get locally. Okay. Other questions? So anybody moving to Seattle just because they got great rocks in Seattle? No. And what you'll find out, though, is a lot of times these rocks will be transported around the country because of this issue. For example, when Trump's building was going in Chicago, there was a big discussion of where they were going to get better rocks to make the concrete even stiffer. Aggregate bond in the interfacial transition zone. One thing that I want to point out before we start getting into production, talk about production issues. One of the things that's the most interesting feature, I think, of concrete is if you just were to look at cement paste and you were to test cement paste and you were to get a typical stress strain curve for cement paste, you would find out that the curve is relatively linear, relatively elastic up until the point where it fractures, and then the crack propagates directly across the specimen. So cement paste on its own, just cement and water, is a linear elastic material, linear up to failure. Once the crack propagates, it behaves much like glass. If you test aggregate on its own, you will notice that it is linear elastic up to a point where it fails, and then typically it's a very brittle material, fails very quickly, and it's a fairly brittle material. There's not a lot of ductility to it. When you put these two things together, you will find the material like concrete, which shows a very nonlinear behavior. So it's kind of an interesting component when you take this cement paste that's linear, the aggregate that's linear, you put them together, you get a material that's nonlinear and exhibits quite a bit of toughness or quite a bit of ductility. And the only way to really think about this is to look at something like the Reese's Peanut Butter Cup. On its own, peanut butter is pretty good. Chocolate on its own is pretty good, but when you put the two of them together, that's really when the magic happens, and you get something that's much, much better. That's what we're looking at here when we start to talk about concrete. It's composite material, and the combination of these two materials enables different properties that we haven't seen before. It's composite action, as I mentioned, the interfacial transition zone, the space where the aggregate attaches to the paste is going to be very important, and typically the ITZ is seen as the weak link. Now, I will point out that this may be very true, or I will also point out that this is a place, anytime you have the interface of two dissimilar materials, it is likely to be a failure plane. So a lot of people have seen things and they have gone on to say, oh, it has to be the interfacial transition zone. And a lot of that can be simply explained by the fact that you have two materials that are connecting, and where they connect is a weak failure plane. Two materials have different elastic moduli, different Poisson's ratio. They move differently, and stresses build up at the interface. Maximum size of the aggregate that's typically going to be used. There are some general rules of thumb. This is going to be designated by the sieve size on which 15% or more of the particles are retained. That's how we determine maximum size of the aggregate. And from here on out, if I refer to it as MSA, MSA is simply the maximum size of the aggregate. We typically want the largest aggregate that we can have. However, there are a few rules that you will want to take note of. These rules come out of ACI. The distance for a slab on grade is somewhat unique. So in the lower right-hand corner, you can see we've got a slab on grade. This would be something like a sidewalk, a driveway. The maximum size aggregate that you can use there is D/3. So if you have a 4-inch thick sidewalk, the largest aggregate that you could use is 1.33 inches. I'm glad someone didn't throw out the millimeters because we'd have to convert it. But it's 4/3, or D/3 is the overall depth. Now, this will tend to be a little larger than we use in most other structures. In most other structures, what we will find out is that the aggregate has to be less than 1/5 of the dimension. And the big reason here is if a slab on grade fails, it is simply going to be supported under the entire slab on grade. All right, a sidewalk fails, and you have two sidewalks resting on dirt. All right. If a beam fails or a wall fails, then it doesn't have the same type of uniform support, and this is one of the reasons that there's a difference in the numbers here. You'll also notice that the spacing between reinforcing bars is incredibly important, and the aggregate has to be less than 0.75 of the spacing so that the aggregate can get through the reinforcing steel and can properly consolidate. Now, one of the things that I will point out is if you're designing a 100-story building, you shouldn't get the reinforcement detailing and go through to try to figure out what's the maximum size aggregate that you can use. Typically, there's going to be a local size that is typically what most people are doing. So the designer will assume, well, we'll get an inch aggregate or an 1.5 inch aggregate and then take it from there. But these are the rules that you need to be aware of. Generally, we want the largest maximum size aggregate that we can because it requires the lowest surface area. And we'll talk more about this, but the surface area is going to dictate the paste that's inside of the system. So if you want to minimize the amount of paste, minimize the amount of cement, you want to use larger aggregate. Aggregates can come in a variety of shapes. I have thrown this in so that you can look at all of the different shapes that are out there. I'm not going to ask you, I would never give you a quiz question or a test question on the 10 different aggregates and tell me what their shape is, because most of the time you can look at them and get a pretty good idea of what the aggregates look like. The bond is better for a more angular or crushed aggregate. This shouldn't be surprising. A smooth or rounded aggregate doesn't stick as well as a crushed aggregate. There should be minimal flat particles, and when we're talking about flat or flake particles here, we're talking about something with an aspect ratio of 3:1. One of the things, for those of you who will work in the state of Indiana, one of the things that you will find out is that there is one particular size gradation that tends to have a lot of flat and elongated particles. It's a size gradation that's very difficult for producers to produce when they make concrete, because all of the good rocks in that size range, they are skimming off to make hot mix asphalt. So what you will find out is in the number 4 and number 8 range, there's a lot of real flat little tiny rocks that don't provide much in strength, are very elongated, and can cause some problems. The more angular the rocks, the more difficult the mixture can be to pump, so you may need to spend a little bit more time working on that. And obviously, like anything else, the finer the particle, typically the more you have to crush it, the more energy you're going to spend. The more energy that goes into crushing it, the more expensive the material is going to be. Aggregate packing is somewhat interesting. This will be sort of the heart and soul of what we talk about for the next week. If you took a bunch of rocks and just dumped them into a bucket and they were all the same size, you would find out that at about maximum packing, you would have 68% of the system full of rocks. All right, this doesn't only hold for rocks. This holds for oranges at the grocery store, basketballs at Walmart, anything that's round and of one particular size. About the maximum that you could get in the system is about 68% by volume. That would mean that the paste in the system would need to be 32%. Quick with the math. So the rest of it would need to be 32%. And we talked about mixtures where we got to much lower than that. When we were on that first slide. So what we typically want to do is we want to use a collection of different size particles to try to make the system more dense. The smaller particles can fit in between the larger particles and can really occupy some of the space in the overall system. And the simplest way to think about this is when you've got, at holiday times, you've got those buckets of mixed nuts around. Right? The little tiny peanuts will find their way in between all those nasty big nuts, the ones that are not that good tasting. At the end of the day, the size of the nut bucket is going to be about the same, but somebody dug through to get out all the nice peanuts and cashews and things like that, and you're just left with those big honking brown nuts that nobody seems to like. Right? The basic idea here is you want to mix sand in up to a certain percentage. That percentage is usually going to be somewhere between about 30 and 50%, depending upon the shape of the aggregate. If you mix sand in up to that amount, the percentage of voids will be about at minimum. And this is something that if you really wanted to do, you could do at home on your own. You could take a bucket or a can and start mixing in different size materials. And what you'll find out is that if you have only one size material, you're up in this 32, 36, 38% range. If you get all sand, again, you're back to sort of a mono-sized aggregate. All right, single-sized aggregate. But really, if you get a good mixture, good gradation, you can minimize the amount of voids in the system, minimize the amount of paste that we're talking about in the overall system. So to really drive this home, this is one of my best animations of the day. So if you didn't pay attention to the rest of the show, this is where all the effort was put in on all of our fantastic graphics. We've got coarse aggregate going into a beaker, fine aggregate going into a beaker, and my cleverly disguised combined aggregate, which is coarse and fine aggregate going into a beaker. If you wanted to find out the leftover void space, you could dump in a fluid. So that fluid could be water, could be any other fluid you want, but why waste anything other than water to fill these up? If you fill them up and then figure out how much water was there, it's a measure of the voids. What you will notice is when you've got the combined aggregate grading, you will see that there's a substantial reduction in the void space. Now in this case, it's the amount of the system that's filled up with water. In concrete, it's going to be the portion of the system that's filled up with paste. So if you want to minimize the amount of paste that's inside of the system, one of the goals is to really get a well-graded aggregate system so that you can minimize the void space. What we are really just after is having enough paste in the system to glue the rocks together. So the overall idea is we want to have a thin coating, around the aggregates that allows these rocks to be glued together. That's really what we're after. That's really the key issue. Now, I will point out here something, and we'll keep coming back to this, and I think I've used different colors each time we've made these great big things. One of the things I had to do this semester was I had to get rid of the white backgrounds as much as I possibly could, because apparently it's easier to sleep when you're looking at the black background, and my voice is more soothing when there's a black background on the sides. So it really enhances the video aspect of this. But this thing looks like a great big orange now that I look at it on the back screen there. So if we have one big aggregate, the surface area is pretty easy to determine. We could say that the aggregate is square, it is d high, it is d wide, so it has 6 surfaces. So if we wanted to calculate the surface area, it would be 6d squared. If we cut the aggregate in half, so we go from something that's, let's say, in this case we have an aggregate that is a 1-inch aggregate, would fit through a 1-inch sieve. All right, and we cut that down to something that's like a 1/2 inch aggregate. All right, so we cut it down to half the size. What happens to the surface area? Well, we now have a cube. Again, it still has 6 sides. On those 6 sides, each one is d over 2. If we added all those up together, we took all 8 of them, we would find out that the total surface area of this aggregate is 12d squared. Now, other than showing off my understanding of general geometry, what is this important for? What do we use this for? Well, one of the things that I will point out is that every time you did gradations, you've done gradations, every gradation is about half the size of the next sieve that you're going to use. So if you remember back to your undergrad class where you took a bunch of rocks and put them over top of sieves, what you would notice if you got real close and personal with the sieves is that every other sieve was about half the size of the sieve above it. So you went from the number 4 sieve, which was 4 lines per inch, to the number 8 sieve, which was 8 lines per inch. So you went from something that was about a 1/4 inch to something that was about 1/8 of an inch. The next size one down was the number
16.
16. So from 4 to 8 to 16. The next one down was
32.
should have been 32, but it's actually 30. All right. Generally, as you go from one sieve to the next sieve, you're cutting the size of the aggregate about in half. Every time you go to an aggregate that's about half the size, you double the surface area. Now, if you think back to our previous slide, we said we wanted to coat the surface area with a thin film of paste. Every time you use an aggregate that's half the size, you double the surface area. The finer the aggregate, the more surface area. The more surface area, the more paste. Okay? The more paste, not always necessarily the more better. It was a Spike Lee reference for anybody who didn't get it. Aggregate size, air and water to cement ratio. So here is an illustration of the information that I just mentioned. On the x-axis on these graphs, you will see aggregate size. This is the maximum size of the aggregate in inches. On the y-axis, you will see on the graph shown on the left-hand side, you'll see the total volumes of the different materials. You'll see the volume of water, the volume of cement, the volume of air, and then the remaining portion here is the volume of aggregate. And what you will notice is as we go from large aggregates to smaller aggregates, you will notice that the volume of the aggregate decreases substantially. The volume of the aggregate is decreasing because the amount of surface area is increasing. We've got to coat that with more paste. You will see that the paste portion starts to grow as we go to smaller sized aggregates. Now, there may be a few of you saying, well, that's great, but I would never imagine us using an aggregate that's bigger than about an inch or an inch and a half. Right? Most practice is below about an inch and a half. There's a little bit of discussion going on now to getting up to 2-inch or 3-inch aggregate for pavements. Where would we use something that's got a 3-inch, 6-inch, or a 9-inch maximum size aggregate?
A dam.
A dam. So the Bureau of Reclamation is really excited about, or at least for a long time was really excited about these really large aggregates. Although we don't do a whole lot of testing with them, because if you had to prepare a specimen with a 9-inch aggregate, a specimen would be how big with a 9-inch aggregate? Huge. We could probably quantify it by using what we used earlier in the semester or earlier in this lecture. For a cylinder to meet ACI's recommendations on how big it needs to be representative, the aggregate needs to be a fifth of the dimension. 5 times 9 inches is 45 inches. You're looking at a cylinder that's 4 foot in diameter, 8 feet tall. That's a big cylinder to be testing. All right, quality control gets a little tricky when we start looking at that. All right, again, you will notice that the water content in these mixtures, all right, increases substantially. The water content is another indirect measure that we'll keep using to talk about the volume of paste. If we talk about the influence of aggregates, finer aggregates will tend to help us out because they will increase the strength. But a lot of times if we make the aggregates smaller, we end up with higher water to cement ratios, more paste, so we can end up with some durability issues. What I want to get into, and we'll start a little bit of this discussion, is how aggregates are made. And I will use 2 separate quarries, and I will try to showcase both of them. One is one that I endured 4 summers at. Another is one from a former student, so I thank him for that. The quarry out of Mexico is a little bit more interesting to look at because you can get in and you can get up close and see a lot of things, because there aren't a lot of things like safety devices in the way. So you can get a little bit more close and personal and see what the crusher is actually doing, and they've got a little bit better pictures. The quarry on the right is a quarry that mainly is feeding the asphalt plant, which is shown here in the background, but rocks are rocks, and the manufacturer of rocks is about the same for asphalt and for concrete, so we'll talk about that. Now, natural sands, pretty much what you're looking at here is deposits of coarse or fine aggregates. They're typically only going to be sieved or cleaned, and they're ready to be used. You may hear people talk about washing these. They'll be putting them through like a cyclone or something like that to spin out organic particles, or to use centrifugal force to get rid of other things. You may see them blending these or dry sifting them, but in general, producing natural aggregates really isn't that difficult. What I'm going to talk about here is the process of crushing aggregates, where they blast them. They're going to crush them using different types of impact, either jaw or impact crushers. They'll separate them out by different sizes and screen them, and we'll get into some of the issues that come with dust control, stockpiling, things like that. First thing you need is a large source of aggregate. These are the mountains outside of Monterrey, Mexico, and what you will notice is there's a large source of aggregate, and it looks like Big Ten football down here. There's a cloud of dust going on. This cloud of dust is the slow capture of this mountain and converting it back into aggregates for the use in concrete. So you need a really large source of aggregate because of the amount of aggregate that's being utilized. One of the first things that's going to be done to get in and start quarrying this aggregate out is drilling and blasting. So much like we saw with the manufacture of materials to go through the cement kiln, here they're going to be drilling. They're going to be drilling a series of holes. Those holes are typically going to be filled. When I say filled, they're not filled up to the top. We're not filling them to the brim with a charge. They're typically going to be filled up about 15 to 20% with an explosive, and then that's going to be detonated. They will typically have a slight angle to the detonation, and the slight angle is to drive the force of the blast back into the face of the rock. So rather than blasting to shoot everything out across the quarry, they are trying to get the energy to go back into the rock and trying to drop that rock straight down because it's a lot easier to pick that rock up. I will tell you that the quarry that I worked at on one particular occasion, the drilling crew had the angle all right, they had the direction all wrong, and it's a big cleanup issue when you project the rock to blast across the quarry. There it was about a $2 million cleanup issue, not only from cleanup, but the plants and the trucks that they crushed in the process of doing it. So being cognizant of what's going on is incredibly important. Here you can see the blast going off, releasing some of the dust. It's not like the films of the Hoover Dam you see where they're blasting rocks off of the face and there's smoke and rocks shooting out all over the place. Typically it's a much more controlled fashion because most of the plants that you're looking at are somewhat around people. And one of the things that people who live next door to quarries like to do is they like to call the quarry and they like to complain about 2 main things. They like to complain about the jiggling and the sounds that are going on inside of their house, and they like to complain about dust. one of the things that I was on each time we would blast, and we would blast once a week, I had the opportunity to take a little seismograph and go sit in the apple orchard that was right on the other side of the where we were blasting and monitor to make sure that all the little apples would be safe. If the blast was too high, as it had a tendency to happen, the little apples would become excited and jump off of the tree. The owner of the apple orchard was not very excited when all the little apples jumped off of the tree, and this was a major PR issue for the company that was working there. Secondary thing, we'll look at taking some of these larger aggregate. Typically, they wanted to blast them into about 18-inch, 24-inch sections, and they would be crushed down. Here's a little thing for you to think about if you don't really feel like studying this evening. The entire time I was there was a person who worked in this machine, and this machine would crush these larger rocks down into smaller rocks. 14 to 16 hours a day, 7 days a week, a person would sit here, raise a very large object onto a rock, and make 2 very small rocks out of it. Gives you a little bit of an idea of what you may want to do when you're studying this evening, because it's cool for 10 minutes. It gets boring after that. We'll pick up here in our next lecture. You would not have to come in on Friday. If you want to get up and leave and come back on Friday, that's fine. If you want to use the address that you were sent and watch it while you're sitting at home, that's fine as well. But it's going to be like a regular time. So it's up to you.
As in Wednesday, 2 days from now, Wednesday, ACI, the American Concrete Institute, Purdue chapter, is going to have a meeting. It'll be 6:30 in Civil